Okay, so this is the last lecture, final lecture of the course, lecture 27 on the PCP theorem. So I'm going to try to sketch to you this famous theorem in CS theory. Okay, so as always, I'll just start talking. If you have any questions, feel free to type them into the chat or interrupt. So this is just a sketch. In one lecture, I'm going to try to tell you a little bit about how the proof goes. A million years ago, together with Professor Venkat Guruswamy, I co-taught a course about the PCP theorem, and you can see the lecture notes for that if you Google the information, which is currently on the screen. Okay, so what is the PCP theorem? We mentioned it a couple times before in this class, but we'll really get into it today. First of all, what does PCP stand for? It stands for probabilistically checkable proofs. And it's a real gem in computer science theory. It's considered one of the most famous theorems in the field. It was originally proven in the early 90s in sort of a succession of works by Feige, Goldwasser, Lovaas, Safra, Szegedy, Arora, Sudan, Arora, Lund, Motwani, Sudan, Szegedy. And it's quite a difficult proof, and like the concatenation of all these papers is 150 pages or something. It's considered quite challenging. But then everybody was real excited in 2005. I remember sitting in my apartment in Seattle when I checked the internet and ECCC, and I saw this paper. It's like, oh, I got to drop everything and read this paper by Irit Tanur, where she gave a new proof of the PCP theorem that was way shorter. It was like 25 pages or so, which is really a totally different proof. What's interesting, and part of the reason I want to present it, as the final lecture, is that it's really only shorter, assuming you have, CS theory in your pocket. So what people liked about it is, if you kind of have a baseline, amount of knowledge about computer science theory, all these tools in your toolkit, then her proof was quite short and not too bad. But it really combines a lot of stuff. I mean, we're going to see some spectral graph theory, some Fourier analysis of Boolean functions, error correcting codes, expanders, CSPs. It's all going to come together in a glorious synthesis, and we're going to prove the PCP theorem using all these tools. So it's kind of a nice way to, I don't know, recap and mention a number of things we talked about in this course. Okay, so what is the statement of the PCP theorem? There's many slightly different equivalent statements. I'm going to give you one that's a bit different from the one that I mentioned in previous lectures, but I'll then tell you why they're all really the same theorem. So the PCP theorem is an NP hardness result for a specific problem, and it says the following. It says there's an absolute universal constant epsilon naught greater than 0. And so think of it in your mind as 1% or something, but really just a fixed constant, such that the following problem is NP hard. Okay, and this is the problem. You're given as input a 3 coloring problem, but think of it like a CSP, like a maximization problem. So I called it max 3 coloring problem, G. This is my weird handwriting font for G. Hope you can get used to that. So you're given a 3 coloring instance G. It's NP hard to distinguish between two cases. First case is where the opt is 1, which, in our CSP notation, this means there is a perfect assignment, i.e. the graph is 3 colorable. You can 3 color the vertices such that all edges are bichromatic, versus the case where the opt is at most 1 minus epsilon naught. So think of that as 0.99 or 99%, meaning that not only is the graph not 3 colorable, but any 3 coloring of the vertices will make at least 1% of the edges bichromatic. You'll only get 99% of the edges at most. I should have said monochromatic there. You'll only get 99% of the edges at most bichromatic, like you're supposed to in coloring problems. Okay. Right, so as I said, this opt is the maximum over all 3 colorings of the vertices of the fraction of bichromatic edges. But it's going to be convenient for us to look at the difference of this quantity from 1. Okay, so I'm going to introduce some non-standard notation here for any CSP at all, script G, not necessarily 3 coloring, but think of 3 coloring for now. I'm going to write badness of G for 1 minus the opt. Okay, so this is sort of the least error you can incur, or at least loss you can incur by an assignment. So in the context of 3 coloring, or max 3 coloring, if I give you a graph G, what is its badness? It's just, the minimum over all 3 colorings of the vertices of the fraction of monochromatic edges. Okay, so these are the violated edges in the 3-coloring CSP. Okay, I'm just changing the notation up here, saying that you know, what's hard to distinguish, and be hard to distinguish under the PCP theorem, is the case where you're given a graph where the badness is 0, meaning there is a perfect 3-coloring, versus the badness is at least this, epsilon 0, like 1%, meaning every 3-coloring of the vertices has to monochromely color an epsilon 0 fraction or more of edges. Okay, and the proof that I'm going to sketch for you actually yields like a very pathetic constant. Like I don't know if I'm not even going to work through the numbers, but it might give you something like 10 to the minus 20, which is horrible. But the point is, it's like a universal constant independent of n, the size of the graph. In case you're curious, the best known epsilon naught that is proved these days is any number less than 1/17. Or think of it like 5%. Okay, so 0 versus 5% is now known to be NP-hard. That's a result proven by Austrian, Tan, Wright, and yours truly in one Magic Summer in 2012. Okay, but let's not worry about the constant too much, but just think of it as a fixed constant in your head. Okay, so it's an NP-hardness result. Okay, so it's just like those classic NP-hardness results, you proved as an undergrad, just much more complicated. And so it's a polynomial time reduction from an NP-hard problem, let's say the most canonical one, circuit sat. And so it takes a circuit sat instance, which is a circuit, C, and outputs a 3-coloring instance, G, so it converts circuits to graphs. And it has the following theorem. I mean, this is the key aspect of it, that two cases. If C is satisfiable, then the graph that's output has a perfect 3-coloring. And if C is unsatisfiable, then every 3-coloring makes at least an epsilon naught fraction of edges monochromatic. Okay, so badness is at least epsilon 0 when C is unsatisfiable. Okay, and this is in contrast to the classic NP-hardness result for 3-coloring as normally understood, which would look exactly the same, except that this would just say the graph is not 3-colorable. But here it's saying not only is it not 3-colorable, like it's very not 3-colorable. Any 3-coloring violates at least epsilon 0 fraction of the 3-coloring constraints. Okay, and therefore, if you could tell the difference between these two kinds of graphs, you could solve circuit sat, and P would equal NP. Okay, so there's the statement up there. And now let me try to answer this question. Why is this called PCP theorem? Like this is, PCP stands for probabilistically checkable proofs. Like what does this have to do with proofs or probabilistic checking or what? So I won't dwell on this too much, but let me try to tell you a story that illustrates why this result is super cool and has something to do with probabilistically checkable proofs if you look at it from a certain angle. So, okay, let's assume we've proved this theorem. And so we know this cool polynomial time reduction from circuit sat to 3-coloring. And now, let's consider a particular circuit C. Let's consider a circuit C which checks if its input is a proof of the Riemann hypothesis or some famous open problem in mathematics. Okay, so there's a lot of work these days on formalizing mathematical proofs by computers so that they're machine checkable, and there's lots of systems for doing this. And you can easily cook up, a circuit that checks if the input string is an encoding of a proof of the Riemann hypothesis in, some standard proof system. Okay, and that's nice because, okay, a proof could be any length, but you might say I'm only interested in proofs that are at most 1 billion bits long. So C might have like 1 billion bit inputs. So great. So now let's say you're the editors of a journal, fancy math journal, and perhaps somebody comes along and says, "Hey, I've proven the Riemann hypothesis. I would like to submit it to your journal." Well, you could say, please code up your proof in a machine checkable format, and then I'll pass it through this circuit and check your proof. And that's reasonable, right? Extraordinary proofs require extraordinary claims, or claims require extraordinary proofs. So, we can make the mathematician work a little bit harder by encoding the proof formally. But you can do an even cooler thing. That's kind of a funnier thing, which is you can say, you know what? Don't give me a bit string that satisfies this circuit C. Please instead give me a 3-coloring, a perfect 3-coloring of the graph G that you get out of running this reduction. Okay, so I mean, you can publish the circuit C to everybody. You can publish the circuit G to everybody. It's produced by a polynomial time reduction. And it's actually not made clear in this theorem, but it's also true that there's a polynomial time algorithm that in this case, where C is satisfiable, if you have a string X that satisfies C, there's a polynomial time algorithm that translates it into a perfect 3 coloring of G. That part of the proof is actually easy. So you can say, hey, mathematician who claimed to have proven the Riemann hypothesis, don't give me a proof that I can feed into C. Instead, work a little bit harder, run your polynomial time reduction, and give me a 3 coloring of this graph G. Okay, it doesn't look like especially interesting because, then the journal can be like, all right, I will now take this 3 coloring you've given me and, check if it's a perfect 3 coloring of G. But, a lazy journal reviewer can do a cooler thing, and this is where like the name probabilistically checkable proofs can come in. They can spot check it in an extremely remarkable way. You see, if the mathematician is correct and they had a perfect proof of the Riemann hypothesis, then this graph would be perfectly 3 colorable, and like the 3 coloring they sent you would, make all the edges monochromatic or bichromatic. But if the mathematician had a mistake, a proof, like a wrong proof of the Riemann hypothesis, even if it, was different, had a Hamming distance 1 bit from like a correct proof, even if it was like, slightly wrong in the slightest possible way, the graph would have the property that, if the Riemann hypothesis is, I suppose, okay, you have to actually add a little bit onto this, but it will have the property that when you run this reduction, every wrong proof will actually make monochromatic like an epsilon naught fraction of edges. So like, think of that as like 5% of the edges. And now what a reviewer can do is randomly pick a constant number of edges from this graph G, let's say 100 over epsilon naught, or 2000 if epsilon naught is 5%, and just look at the 4,000 different endpoints colors, and just check that each of these 4,000 or 2,000 pairs are distinct. And if they're all distinct, then the reviewer can be confident that, except with probability like e to the minus 100, the proof is correct. So you get this amazing spot checkable proof where you just have to look at 4,000 symbols, red, green, or blue, from the proof, and you can be highly confident whether or not the mathematician had a correct proof that satisfied the circuit. So that's why it's called probabilistically checkable proofs. But that said, that was actually how it was originally conceived, but people eventually realized it was kind of equivalent to this much more mundane thing, the NP hardness of sort of approximately solving satisfiable CSPs like 3 colorability. There's a question, are such circuits easy to construct? Yeah, well, this is getting a bit more into mathematics formalization, but if you have like a mathematics verification system, like these ones that exist like Agda or Lean or whatever, Coq, then they have like a small set of rules, and so you just need like a circuit that first checks that the proof is trying to prove the Riemann hypothesis. So the statement of the theorem of the proof is the Riemann hypothesis, and then it just has to check that each of the deductions in the proof follows from this short set of valid deduction rules in the proof system. So in principle, yeah, it's no problem to construct these things. And actually, PCPs these days, all these constants I'm going to show you are horrible. You'll see some numbers like 10 to the minus 20 and things that are much worse. But actually, people are using PCPs these days for cryptographic applications that are actually practical. So it's pretty cool stuff. Okay, so that's all I want to say, though, about this proof checking mentality. And we'll get back to just thinking about CSPs. So one thing I want to say is that it's not important that the CSP here that we're talking about is 3 coloring. That's just I chose it for convenience. But you could have any other non-trivial CSP here and get essentially a similar result. So every time I stated the PCP theorem in previous lectures, I actually stated it for 3 SAT or max 3 SAT instead of max 3 coloring. But it's equivalent. And I'll show you one direction of the equivalence, or sketch one direction of the equivalence. Let's say you wanted the exact same theorem, but you wanted to be talking about max 3 SAT here instead. So to conclude that, it's hard to distinguish between the case of a perfectly satisfiable 3CNF and the 3CNF where the best assignment satisfies at most 99% of the clauses. Well, what you can do is first get this PCP theorem about 3 coloring. And then we know from, our undergraduate days, our textbooks, that there's like a, a many one polynomial time reduction mapping three colorability to 3-set. That's just by virtue of the fact these are both NP-complete problems. But, okay, so this takes a graph and outputs like a 3CNF phi. But what you can also observe if you take a look at the reduction in the textbook is that it's a particular kind of reduction like a gadget reduction, which basically means like given the graph G, you make a 3CNF where like for every vertex in G, you like kind of encode it by like 1 or 2 or 3 variables in your phi. And then for every edge or every constraint in the graph, you kind of convert that edge to like 3 or 6 or 8 or something, 3CNF clauses. In such a way that you're really like, there's like a one-to-one correspondence between assignments and colorings, and like, the constraint that the 2 colors on an edge are different, and like the satisfiability of like these 8 gadget clauses you introduce. Point being that like on one hand, if you have like a perfectly 3-colorable graph, this reduction produces a perfectly satisfiable 3CNF formula. But, and I leave this as an exercise, you can conclude that if the graph is not 3-colorable, but has badness at least some epsilon 0, then the badness of phi will be, I don't know, like at least epsilon 0 over 8 or 10 or 20 or over some constant. Okay, and the point is like, you just have to observe from the reduction that like, if you had some assignment to phi, you could translate it back to like a coloring for G. And this coloring for G, if you're in the case where G is not satisfiable, has to violate at least an epsilon 0 fraction of the edges. And then for each violated edge, you can infer that at least one of the associated 3CNF clauses would also have to be unsatisfied by the assignment you started with. So basically for every unsatisfied edge in G, you get like 1 out of 8 or 1 out of 10 or something unsatisfied clauses in phi. Okay, so this epsilon 0 goes down by a constant, but you can pass from one constant to another. Okay, and basically this holds, it sort of formally holds by the dichotomy theorem for any CSP that's NP hard. There's a gadget reduction between any 2 CSPs that are NP hard, and therefore this kind of translation holds, just this constant epsilon 0 might change. Okay, but for simplicity, we're going to formally stick with 3 coloring in this lecture. I also want to mention that there's nothing special about starting with circuit sat here. This is just an NP completeness result or NP hardness result. So you could have started with any. I mean, the PCP theorem would be equivalent if you put any NP complete or NP hard problem on the left-hand side here instead of circuit sat. Just because it's NP hardness results, it doesn't matter what NP complete problem you start with. In particular, I'll make a funny observation, which is one NP complete problem we know is 3-colorability. But like the classic version of just trying to distinguish 3-colorable versus non-3-colorable. So you could put 3-sat here, but as I said, you could also put 3-coloring, which would be kind of amusing. In fact, that's what we'll do. This is like the final form of the PCP theorem that we'll prove. We'll show that there's sketch that there's a polynomial time reduction from 3-colorability to 3-colorability, like from graphs to graphs. But with this sort of property that it's sort of badness amplifying. So, if you take a graph G that's 3-colorable, and pass it through the reduction, you get another 3-colorable graph. But you take a graph that's just not 3-colorable, but maybe it's almost 3-colorable, you get a graph that's sort of far from 3-colorable. Okay, so this is the inherent nature of the PCP theorem. Okay, or to just summarize the notation, it looks like this. Okay. And now I'm just going to make one small observation that like if you have a graph G with n vertices and m edges, to say that the badness is at least 0 is equivalent to say that it's at least 1 over m. That's a very trivial comment. It's just that like if you have a graph that's not 3-colorable, it means that every 3-coloring of the vertices must make monochrome at least 1 edge, which is a 1 over m fraction of all edges. Okay, so this is really, if you phrase it in this way, it's really like a badness amplification theorem. In Rita proof, she used the term gap instead of badness. It's a slightly stater thing, and she called her proof like a proof by gap amplification. And this is how Denor's proof goes and how I'll sketch it to you. I know, like when Irit, sometimes gives a talk about this result, she uses this analogy. You see, the reduction has to transform a graph into another graph in polynomial time, such that if like it's slightly not three colorable, it becomes highly not three colorable. But if is three colorable, it stays three colorable. And so the poor polynomial time reduction is just polynomial time. It cannot tell what case the initial graph is in, whether it's three colorable or not. But it has to do some operation to it such that, if the graph is not three colorable, it really spreads out like the badness. So her analogy is like, like you're given like a piece of toast, and it has like a teeny spot of jam on it potentially, or maybe it has like the jam is like the badness. Maybe it has no badness, but maybe it has like a teeny tiny spot of jam on it, and you're not allowed to look at the toast, but you have to do like some operation which will spread out the jam if it exists. So the operation is to just like somehow in real life, take your knife and like just rub it all around the toast. And then wherever like the tiny bit of badness is, it gets like spread out. But of course, if there's no badness at all, then, rubbing your knife all around the toast doesn't do anything. I don't know if that analogy helps. I probably only gave like a poor version of like Irit's version of this analogy, but I liked it. So her proof goes not by trying to prove this in one shot, but by sort of the slowly, gently method of building up to it in stages. So the main thing she proved, and the main thing that we'll try to sketch, is a badness amplification theorem that looks like the following. So this is a new theorem, which is going to imply the PCP theorem. It says there are universal constants, epsilon 0, and some big constant k, and a polynomial time reduction r. This r will not be the final r, but some polynomial time reduction r that maps three coloring instances to three coloring instances. So it takes a graph G and outputs a graph G prime with three properties. So property one is that the size blowup is just a constant factor, this fixed constant k. And when I say size here, I really mean like the number of bits it takes to write down the instance, which is basically like the number of edges and vertices in the graph. So this reduction will take a graph and produce a new graph that has more vertices and edges, but everything will be within like a fixed constant factor. Two, it'll have the classic property of these reductions, just that if the graph G is perfectly three colorable, then the output graph G prime is also perfectly three colorable. But the main property, well, together with the first property, is this, that this reduction R increases the badness by a factor of 2. Well, you can't literally say it always increases the badness by a factor of at least 2, because the badness can never be at most 1. In fact, for three coloring, the badness can never be more than 1/3, because there's always a coloring of the vertices that falsifies or violates at most 1/3 of the edges, because a random coloring will have this property in expectation. So if the badness is already high, then you cannot like make it go up by a factor of 2. But it says as long as the badness is lower than this epsilon naught, this fixed constant like 1% or whatever, this reduction R like at least doubles the badness. Okay, that's not inconsistent with bullet point 2, by the way, because if badness of G is 0, it stays 0. So this only increases the badness by a factor of 2, whereas in the PCP theorem we want to get it up from 1/m to epsilon 0 constant. You can probably guess how this is going to go, though. The key aspect of it, though, is it's really strong on this. It only blows up the size of the instant by an absolute constant factor. So perhaps you can let me know in the chat like how you would take this badness amplification theorem and use it to conclude the PCP theorem. Repeat amplification. Yes. How many times should you repeat it? Keep an eye on the chat window here. Log m. Yes. Very good. So this badness amplification theorem implies the PCP theorem because, to get this final polynomial time reduction, given your graph G, you just do this reduction R that doubles the badness like log m times. Okay, and you do it log m times, and the badness either stays 0 the whole time in case 1, or in case 2, it starts out at 1/m, but after doubling it log m times, it gets up to this universal constant. Basically this point, at which it stops doubling. And what's great is, here it's very critical that the size blow up is only like linear. The size blow up is this constant factor k to the power of log m. Log m, the number of edges at most of the number of vertices are squared. So like log m and log n are the same up to a factor of 2. So the overall size blow up is a constant to the power of order log n, which is poly n, which is great. So all the time you're applying this, subreduction r, everything is staying polynomial size all the way to the end. So definitely a cool strategy, which was quite different from the original strategy for proving the PCP theorem, which involved like, I think it involved like 2 recursive steps instead of like log m recursive steps. Great. So the goal for the rest of this lecture is to sketch this proof of this badness amplification theorem. Okay, so if there are any questions, please do let me know. So the nurse method for proving this is also really cool. She does not do it just in one shot, one big reduction R, but her reduction R is a combination of 4 steps. 1, degree reduce. 2, expanderize. 3, power. 4, mini PCP. So I'm going to talk to you about all of these steps, but these are 4 algorithms, reduction algorithms, that you put them all together, they achieve this badness amplification algorithm R. And some of these steps are more important than other steps. So these first 2 steps are kind of straightforward. I say straightforward, I mean, I'll sketch the proof of like them. They won't be that straightforward, but they were kind of known already, or like, well, these are standard sort of ideas by the time de Noort proved her theorem. The main step is this power step. This was like our main innovation. This is actually the step that really does this badness amplification by a factor of 2. This power step is the main innovation. It's very cool. And, it only works to increase the badness by a factor of 2 if, your underlying instance has been expanderized. So that's like the whole point of steps 1 and 2 is to sort of turn your CSP into like an expander CSP, and then this power step will work. But this powering step screws up some other parameters. So it increases the badness by a factor of 2, but as we'll see shortly, like it sort of ruins several other aspects of the reduction. And then this like mini PCP step like fixes some of them. And this mini PCP step was also sort of partly innovation in de Noort's proof as well. It's partly an innovation, partly kind of already known. So also cool, but like this is the most cool bit and what we'll spend the most time talking about. And I should mention that, okay, this overall R is a reduction from 3 coloring instances to 3 coloring instances. But as you do these steps 1 through 4, in the intermediate stages, you will no longer have a 3 coloring CSP. You will have different kinds of CSPs. These will actually still be binary CSPs, meaning that each constraint will involve exactly 2 variables. And therefore, it will always be good to think of these CSPs as like graph CSPs, where like the variables are vertices and the edges are constraints. It's just that the constraints might not just be like the standard coloring constraints, like, the 2 endpoints should get different colors. That's the coloring constraint. They can have they'll have different constraints. And in fact, even the domain will get larger as we go along, well, throughout these steps are. Particularly the powering step will change the domain kind of drastically, meaning that you won't be assigning just red, green, blue to the vertices. You'll be assigning like, from a bigger label set to the vertices, and you'll have like complicated constraints, binary constraints in your CSP. So that'll happen sort of in the intermediate stages of 1, 2, 3, 4, but at the end of 4 and at the beginning of 1, you have a 3 coloring CSP. Okay, so now I'm going to give you the overview of like what the point of each of the 4 steps is. And, but I won't say how to do the step. And then we'll see that if we can implement each of these steps, we'll get the badness amplification theorem and hence the PCP theorem. And then I'll tell you some details about each of the 4 steps. Okay, so the first one is degree reduce. And this takes a CSP, a 3 coloring CSP G, and produces another CSP G prime that actually will still have domain size 3. It'll still have like red, green, and blue as its labels, but it'll have both non-equals constraints, like in 3 coloring, and also equals constraints, which is different from 3 coloring. So the main point of this part of the reduction, as you might guess from the name, is to reduce the degree of the underlying graph. So the sort of starting graph here, G, could have any degree. It doesn't have to be regular. It could have some vertices of degree n. It could have some vertices of degree root n. It could have some vertices of degree 3, whatever. The point of this degree reduction will be to clean things up so that the underlying resulting graph G prime, that should say becomes 9 regular. I don't know where the word regular went. Okay, so at the end of this, every vertex will have degree 9, i.e. it'll participate in exactly 9 constraints. There's nothing overly special about the number 9, just some fixed small constant is the point, but the way I decided to describe it, it was going to be 9. Yeah, this is funny without the word regular. Anyway, so that would be the effect. Now, unfortunately, this, oh, there's a question I'll get to in a second. Unfortunately, this reduction that gets things down to degree 9, 9 regular graphs, will have some side effects that we'll have to tolerate and fix later. Okay, let me check out the question. It says, do all known proofs incur a log n blowup in the size of the output graph? I'm not sure what you say. Oh, do you mean for the final blow up in the PCP theorem? So with this version of the PCP theorem, the final blow up is like a huge polynomial because you multiply by this factor k, which might be like 1,000,000. It's actually much bigger than that, log n times. So the blow up is like n to log 1,000,000. So n to a huge constant. We mentioned last time that like Moshkevitz and Raz have a better version where the blow up is quasi-linear. It takes instances of size n, produces instances of size n to the 1 plus little of 1. I think the smallest known log little of 1 factor, actually I'm not sure what it is. I think it's polylog n. But it's a major problem actually, whether you can have like a linear size blow up in the PCP theorem. That's unknown. Good, so let me, hope that answers the question. Let me get to the side effects. So, okay, one side effect of this degree reduction is the size of G prime is bigger than the size of G by a constant factor K1. That's totally fine. We're planning on blowing up size by constant factors, so that's no biggie. This reduction does not change actually the size of the domain, but it does add equality constraints, as I mentioned. So this new CSP G prime has both edges labeled not equals and edges labeled equals. So you're trying to make some edges bichromatic and some edges monochromatic. It has a property that preserves perfect satisfiability. So if G is perfectly 3-colorable, then this new G prime will also be perfectly satisfiable. And all the steps, all these reduction steps are going to have this property. So I'm going to basically stop mentioning it. You can assume all the reduction steps have this property. And the final property is that the badness of G prime will always be at least the badness of G divided by some potentially big constant C1. Now this looks funny because it looks like the badness could also actually go down by a constant factor. Like imagine C1 is 100. And it's true, this operation can make the badness go down by a factor of 100. And the whole point of capital R is supposed to be make the badness go up by a factor of 2. So what's going to happen, and you'll see this over the next few slides, is that step 1 and step 2 and step 4 actually make the badness go down by a constant factor potentially. So that really hurts us. But the point is that the powering step is going to make the badness go up by a big constant factor that we can tune in such a way that the overall badness change will be increasing by a factor of 2. So basically, we're going to tolerate this badness because we're going to fix it, this badness drop, because we're going to fix it in step 3. Okay, so that's degree reduce. Next step, expanderize. So expanderize also takes a CSP, this new kind of CSP with red, green, and blue as the labels, but some equality and non-equality constraints. And the point of expanderize is to output like a new CSP G prime, which will still be a binary CSP, but the sort of underlying graph, the point is it'll be an expander graph. And again, it'll be regular for some fixed small constant, which in my version of the story is 17, but again, don't worry too much about this. So the point is after step 1, you got down to like a regular graph, like an 8 or 9 regular graph or whatever, but it might not be an expander. And after step 2, it'll be an expander graph. And like in order to expanderize, you need to have a constant degree graph. So that's why you did the degree reduction step. Just to remind you, what is an expander graph? It's usually defined in terms of eigenvalues being an expander. So, it means that if you take the graph G prime and its normalized adjacency matrix, K as we've called it, the maximum eigenvalue is always 1, and you're an expander if your second largest eigenvalue is bounded away from 1 by some constant. And it'll again be, bounded away from 1 by some mystery constant like 0.0001, but some absolute constant. Another definition of expanders that's equivalent, as you might remember, is that like every smallish set of vertices has a lot of edges of the graph touching it. So the graph has large minimum conductance. So that's the main effect there. It's setting you up so you can do this power step. And it has some side effects that are the same as the side effects as in 1. So the size goes up by a constant factor, and the badness actually goes down by a constant factor. Okay, let's expanderize. Now the main step, the powering step. And you'll notice that I've actually stuck in like some parameter here, t. So this is a user-selected parameter. The reduction can choose it. And it will eventually be an absolute constant, but t is sort of the amount by which the powering operation increases the badness. So you're going to take t a large enough constant to overcome all the badness losses in steps 1, 2, and 4. Right, so what is the main effect of this powering reduction? It's to increase the badness by a factor of t. Okay, and actually it's, it's like kind of funny. It doesn't increase it by exactly t. It increases it by a factor of t divided by some other universal constant, C3, which I don't know, again, might be like 100 or something. But you can always overcome that fixed C3 by making t a larger constant. And also, as before, right, the badness is always at most 1. So this cannot be literally true. It's only true if the badness is already smaller than this fixed constant epsilon 0. And by the way, this epsilon 0 will basically be 1 over t, where t is whatever constant you choose. So it's preventing you from, getting more than a badness, which is a fixed constant less than 1. So that's the main effect, and that's the main power to increase this badness. And it's like called power, not just because it's like a powerful step, but it's sort of like graph powering. It's sort of like you square the graph, or it's even more like you raise the graph to the power of t. So like the edges are like length t paths sort of in the input graph. But we'll get to that. So this one has some side effects too, and some kind of worse side effects. So it increases the size of the instance by a factor of 2 to the order t. But t is going to be a constant, so 2 to the order t is just a constant. So that's fine. We don't mind constant size increase. Even more notably, the label set in our CSP used to be of size 3, just red, green, and blue. But the CSP output by this powering operation will have a pretty ginormous label set. I use omega as always for the domain or the label set of a CSP. You'll have size that's approximately 3 to the power of 18 to the power of t. So that's big, but remember t is a constant, so it's just a constant. So that's fine. And not only will like the label sets, the thing that you're trying to assign to the vertices in the output CSP G prime be very large, but the constraints, which constrains 2 variables, will be quite elaborate. Well, they're just fixed constraints on 2 variables and label sets of this gigantic size, but they're kind of complicated. Okay, so that's powering. And the last step is mini PCP. And the main aspect of that is to like get you back from this crazy CSP type with huge domain and weird constraints back to the 3 coloring CSP. So that's the point. The main effect is to get the domain size in G prime back down to 3 and back down to 3 coloring constraints. And you might even like kind of see, I'll talk about this a little later, like why this step is called mini PCP. You see, we're starting from like a CSP where like you have these binary constraints, but they're super complicated constraints. Like these things that these constraints that are being checked on the labels are very complicated. So complicated you might need to encode them by like a big circuit. And we're kind of replacing these by just the simple 3 coloring constraints. And that's kind of like what the PCP theorem does, right? It replaces this complicated circuit sat thing with like a three coloring CSP. Well, we'll come back to this. Okay, and this one has some side effects too. This is like the awesomest side effect. The size goes up by a constant factor of something like 2 to the 2 to the 2 to the order t. So merely triply exponential in t. Still constant. I guess this is a good time to remind you that the name of this course is CS Theory Toolkit. And I should emphasize that, the point of this proof is just to prove the theorem, to show that all these constants exist. It's like ridiculously inefficient. You can make this merely doubly exponential with like not too hard of a trick. But as I mentioned before, they're actually not through de Noort, well, actually, yes, through de Noort's proof and some other coding theory-based ideas from the original proof. They're like very practically efficient versions of the PCP theorem these days. But the point of this lecture is just to prove the result in theory. So great, 2 to the 2 to the 2 to the order t, still a constant. And as in steps 1 and 2, this step has the feature that it makes the badness go down by some universal constant factor C4, but we've seen that before in steps 1 and 2. So that's the description of all 4 pieces of the reduction R that achieves badness amplification, this factor 2 badness blow up while only blowing up the size by a constant factor. And so putting all these 4 steps together, I notated here like, it takes a 3-coloring instance G and outputs a new 3-coloring instance G quadruple prime after passing it through these 4 steps. And what are the overall effects? Well, we go from a 3-coloring instance to a 3-coloring instance. Great. The size of the final instance is dominated by the last step. So it's like at most 2 to the 2 to the 2 to the order t times the input size. But we haven't selected the parameter t yet. We still get to. And what about the badness? Well, if you put all the badness statements together, every one of the steps loses a universal constant factor in the badness, C1, C2, C3, C4. But step 3, the powering step, gains a factor of t. And you get to choose t yourself. So you can just take t to be like C1 times C2 times C3 times C4 times 2 to get out this factor of 2. And you accomplish the theorem. So t is just a constant, happily, and the size blow up is also a constant. And all the reductions are polynomial time, and the instance size stays polynomial even after all like the log m applications of this badness amplification theorem. Okay, so this is a great time to stop for questions, because what I'm going to do in the next, in the last half of this lecture is just kind of give you a sketch of how each of the 4 steps of the proof works. Let me also mention while we're here that you should fill in the faculty course evaluations for this course. If you go into the chat, I put the link. And why not do it now? You're sitting in front of a computer. You're thinking about the course. I'm not going to be offended if you're typing into your computer on the side while you watch this lecture. So yeah, why not just do it now so that it gets done? It's really helpful to have these, and it would be great if we could get a 100% response rate, which is rare, but hopefully we'll get it. Okay, well, that was also some chit chat to give you time to ask questions, but I don't see any questions, so I shall just press on. Great, so step 1, degree reduce. So this is actually one where I'm going to go into a lot of the detail, because it kind of gives you some of the flavor of how these reductions work, or some aspects of them. So let's do it. Let's do the degree reduce steps. Remember, main effect is that it's supposed to take a general 3-coloring instance G and produce a new 3-coloring instance G prime, where the graph is 9 regular. And these are the sort of allowed side effects that we're going to tolerate. So what's the idea? It's kind of similar to the ideas that are used in constructing expander graphs in iterative fashions. Like we had talked about this on one homework, this line graph method of Spielman, and in the lecture on expanders, I talked about the zigzag product. Kind of similar. So the idea is you go through every vertex in the input graph G, which could have any old degree D, and different vertices could have different degrees. And you kind of replace that vertex by a cloud of vertices, and particularly replace it by an explicit expander graph on D vertices. That's like 8 regular. So actually, although expanders is not in the name of this step, you also need expanders here. Okay, and we're going to rely on the fact that, as we saw from the expanders lecture, there are polynomial time deterministic algorithms that can give you like a constant degree expander graph on any number of vertices. Actually, the bit about any number of vertices takes a little bit of effort, but let's assume it. So the reason I actually chose 8 through here is like the simplest possible like explicit expander is this one we mentioned due to Margulis and Gabriel. That's like extremely concrete. It's like you have the grid of vertices and you connect up each vertex to 8 others in a simple way. So you can use that construction, for example. I should also mention that like you can get rid of all the use of expanders here in this proof by replacing them with random graphs. The only trouble with doing that is you'll get a randomized reduction instead of a deterministic reduction. And so your conclusion will not be that, distinguishing 3-colorable from far from 3-colorable is hard, assuming P does not equal NP. Your conclusion is that assuming, BPP does not equal NP. That's not so bad. But on the other hand, you can get like a classic NP hardness reduction deterministic using expander graphs. I see a question here. What if there's a vertex of degree at most 8 in the original graph? Yeah, we can let these expander graphs have multiple parallel edges. So it's possible to have like an 8 regular graph on fewer than 8 vertices. And, such graphs will actually not be good expanders, but we really, I'm not going to get into this level of detail, but we really only need like it to be a good expander for like sufficiently large D. And if it's like a poor expander for like constant D, like D equals 8 or D equals 10, the proof will be okay. But let me not get into that level of detail. There's like other like slight annoyances, like this Margulis Gabriel expander really only gives you an expander on a number of vertices, which is a perfect square. So you have to do some hacks to get around this, but let me ignore those. So let me show the picture here. So for the degree reduced step. So here's your graph G. The different vertices can have different degrees. I didn't make the degrees too high here for picture's sake, but it's going to make it a little bit weird. But just use your imagination to maybe pretend these are quite high degree vertices. So this vertex U might have D neighbors, and you're going to do this replacement for every vertex in the graph. And so the new graph G prime is kind of drawn in an ugly fashion down here. Looks like this. You see that like every vertex, I kind of blew it up into like a subgraph. And each of these subgraphs is an expander graph, one of these 8 regular expanders. And if you have D neighbors back here in G, you're going to have D vertices over in this blown up graph G prime. So in this little picture, U had 5 neighbors. So like I had like 5 vertices here. And then I plunked down inside here an 8 regular expander on 5 vertices. Well, that's a little bit funny, but imagine 5 is much larger. If it really does have 5 vertices, then you'll put in, I don't know, you can put in any old graph that's 8 regular, even though it's not an expander when D is so small. You do that for all vertices in U, and that's your final output graph G prime. This is most of the construction. And so one thing to notice is that like G prime has 2 different kinds of edges. It kind of has like edges that correspond to the old edges, which I call the white edges. So like this edge here corresponds to this edge here. And so this is supposed to be a CSP. So they're supposed to have constraints, not just edges. And for the white edges, I'm going to retain the classic 3-coloring constraint that like the endpoints should get different colors. But we also have these like intra-cloud edges coming from the expanders, which I call the yellow edges. And I'm going to put equality constraints on these. So that's the definition of the reduction. It produces a new CSP with some edges, like the old white edges, have non-equals constraints. The new yellow edges have equality constraints. And let's see, so the new graph is 9 regular, because like each of these vertices here is connected to 8 inside edges and 1 like old edge. So that's why it's 9 regular. And yeah, the new domain size is still 3. You're still labeling vertices by red, green, and blue, but we have some equality constraints now. Let's think about the size now. You see, for every vertex here that had D edges, you kind of replaced it with a graph on D vertices, that was like 8 regulars. So this graph here has like 4D edges. So you kind of replace like D edges by like 4D edges or something like that. So the number of edges goes up by a factor of, I don't know, 5 or something. I don't do the calculations exactly right. Maybe it's 9 or maybe it's 2.5 or something, maybe 5. Anyway, the point is it goes up by a constant factor. So that's good. And what's the idea behind this reduction? What's the point of it? And why does it satisfy this simple property? Well, the point is supposed to be that, like, okay, imagine this graph is 3-colorable, G. So there's a perfect coloring assignment, red, green, blue to the vertices such that every edge is bichromatic. Then there will be a perfect assignment to G prime, right? What you do is for each cloud, like this cloud of vertices corresponding to the original vertex U, like in the good perfect coloring for G, if you got red, then what you're supposed to do is put red on all 5 of these vertices here. Okay, and if this was green in the perfect assignment for G, you're supposed to put green on all 3 of these vertices here. And you see that'll be a perfect assignment, right, for G prime, because all the vertices in one cloud get the same label. So all these yellow intra-cloud edges have their equality constraints satisfied. And on the other hand, these old white edges are also satisfied because these white edges are sort of exactly corresponding to edges back in G. And the assignment you're using perfectly satisfied G. So it's also going to satisfy these white edges in G prime. So that's this property here. So this is the main thing we have to worry about. Like, why does the badness only go down by at most a constant factor? So how come maybe you know, you could have the badness go way down. Like there was no particularly good 3 coloring here. Like every 3 coloring for G, you know, screwed up 10% of the edges. But now suddenly there's like an amazing assignment for G prime that barely screws up any edges. Well, basically the idea is that shouldn't happen. So like, roughly speaking, you can kind of look at G prime and consider assignments. And if these assignments like mostly give the same color to like most clouds, like for most clouds, an assignment pretty much uses the same color for all of them, then that'll kind of correspond to like a coloring back for G. And therefore, like most of the white edges will get screwed up. On the other hand, if you don't use an assignment that mostly uses the same color for like within each cloud, then you'll mess up a lot of the yellow intra-cloud edges. That's the idea of the proof. I'm going to write the proof on slides. It's going to be kind of messy, and I'll go a little bit quick because I don't want to dwell on this too much. But that's the idea. So let me messily kind of sketch that in a bit more detail. We're trying to show this thing down here. So let A prime be the best assignment for G prime. Okay, and so it, by definition, satisfies or violates a badness of G prime fraction of the constraints. So these are the white and the yellow constraints. Some epsilon prime get violated by the best assignment A prime. And what I want to kind of do is decode A prime to an assignment for G that we can reason about, a coloring for G that we can reason about. And the natural way to do this is as follows. I'm going to construct an assignment A for G by going through each vertex like U. And what I'll do is I'll look over the cloud for U, which is over here. And A prime is assigning colors red, green, and blue to the vertices in this cloud. And I'm just going to take the plurality color, whichever one of red, green, or blue gets used the most by A prime in the cloud. And I'm going to make that the assignment for U back in G. So in this way, from A prime, an assignment for G prime, I've got an assignment A for G. But by definition, A violates at least, whatever A is, it violates at least a badness of G fraction of constraints in G. So it like monochromatically colors at least the, let me call this epsilon fraction of edges in G. So this A that I've gotten from A prime kind of messes up a reasonable fraction of these original edges in G. And I want to conclude that A prime must be messing up a lot of edges as well in G prime. Maybe the same fraction, epsilon, divided by some universal constant C, C1. So here's the idea. Take an edge in like this original graph, like maybe this edge here, UV, that this assignment A I've got violates. Oh, sorry, I called it U prime. Take a white edge, U prime, B prime, that's violated back in the original graph A. Okay, so this edge exists back in the original graph A. And let's think about some possibilities. what's going on with what A prime gives to U prime and that A prime gives to V prime? Well, if A prime gives to U prime the same thing that A is giving to U, which is to say if A prime's assignment to U prime is like the plurality assignment for this cloud, and that plurality thing also happens for V prime's cloud, then, you know, A prime's assignment to U prime is the same as A's assignment to U, and same for V prime. But U prime V prime is a violated edge for A. So then, you know, U prime V prime is also a violated edge for A prime and G prime. So this violated edge for A translates into a violated edge for A prime and G prime when these two things occur. On the other hand, what if these things don't occur? Well, then for at least one of them, either U prime or V prime, let's say U prime, it means that A prime's assignment to U prime is actually a minority assignment with respect to U prime's cloud. And so what that means is, since overall A violates an epsilon fraction of edges, original edges, you can apply this sort of deduction to each such edge and conclude that either a constant fraction of the white edges over an A prime get violated, so like half epsilon of the A edges white edges get violated, or for the other, or a constant times epsilon fraction of edges and hence vertices by regularity in G prime kind of are minority labeled by G prime. And what we want to deduce in this case is that like if A prime basically creates like a lot of minority vertices U prime that are assigned the minority label for their cloud, then we want to argue that a lot of these yellow intracloud edges, which have equality constraints, by the way, get violated. Now, actually, that might not happen. You might worry that that might not happen because it could be that for this cloud, it has like a lot of minority assigned labels, but they're all kind of like hanging together in like a small set where most of the cloud edges are interior to that set. And then they're like kind of all equal to each other, this little like minority side set. And maybe if they don't have a lot of edges to the majority or plurality vertices, you don't get a lot of constraints, violated constraints. But here's why we've used expanders. This cannot happen in an expander. So this cloud is an expander, which basically means that every set of at most 1/3 of vertices has a lot of edges coming out of it, has high conductance. That's the nature of an expander. So whatever the plurality assigned vertices are, they have a lot of edges coming out of them to the, whatever the minority assigned vertices are, they have a lot of edges going out to the plurality assigned vertices. And therefore, it is true that a lot of these equality constraints get violated. So that uses the expansion property. Okay, so, and you lose like a constant factor because that's the nature of an expander that has constant minimum conductance. Okay, so that's the idea. And if you don't follow all the details, then, well, you can review them later, but I wanted to show most of the details for this one. Okay, so that's actually the end of degree reduction. And we're going to move on to expanderize. This one's going to be a lot shorter. This is the step where we have a regular CSP now, a 9-regular CSP, but we want to make it an expander, like globally an expander. Right now it's like made of these little expander clouds, but we want it to like globally be an expander. And if the original white graph was not an expander, then this new degree reduced graph won't be an expander either. But it's not going to be too hard. So our main effect is we want to make it a 17 regular expander, and these are the side effects. And here's the idea. We have this graph now on like some n vertices. It's like 9 regular. We're just going to take like any old 8 regular n vertex graph called script E and just stick it on top. It's the dumbest possible thing. Just stick it on top. And now we've stuck all these new edges on top, this 8 regular expander on top. We have to put constraints on these edges. And we'll put like the most liberal possible constraints. These constraints are just always satisfied. It's like freebie, like no matter what assignment you put to the endpoints of this edge, satisfied. So, okay, let's see what's going on with these side effects. So, and also the main effect. So the first thing is, well, the main thing to check is that the resulting graph is an expander. So we took like an arbitrary 9 regular graph, and just slapped on top of it an expander that's 8 regular. So okay, that makes a 17 regular graph. That's fine. And I claim that if you take any graph and stick an expander on top, assuming they have about the same number of edges, which they do because one's 8 regular and one's 9 regular, then it's still an expander. Maybe the expansion gets worse by a constant factor. And the point is, E has some, being an expander, has some, positive minimum conductance. Every set of vertices touches at least a 0.1 fraction of d times the degree times the size of the vertex set. So it has a lot of out edges. So every vertex set in E plus G also has like a lot of out edges because it at least has E's out edges. In G, all the edges could stay inside. But, G has only slightly more edges than E because G is 9 regular and E is 8 regular. So the convexance can go down by a factor that's like basically half, maybe a little bit worse. And then if you like the the eigenvalue definition of expanders, then you can conclude still that this is an expander with the eigenvalue definition because of Cheeger's inequality that says minimum conductance and second largest eigenvalue of K prime gap are equivalent up to one is a constant if the other is a constant. Okay, so that's how G prime becomes an expander. We basically just doubled the number of edges, slightly less, so the constant size goes up by only a constant factor. Let's just check these side effects. These new constraints we added are always satisfied. So like if you have a perfect assignment for the input G, you still have a perfect assignment for G prime, you can just use it. And the badness can only go down by a constant factor because, really you've just added like roughly the same number of constraints as you had before that are freely satisfied. But any assignment that violated, 1% of the constraints in G will also violate basically half times 1% of the constraints in G prime because, okay, G prime just has these sort of dummy, half the constraints are like G prime dummy constraints. Okay, so that's it for expanderize. Now I'm going to leave power in step 3, the powering step, and come back to it at the end because that's the most interesting part. So I'm going to skip to step 4, and this is the part that I'm going to sketch the most. I'm really going to just say the highest level words about this, even though it's like a non-trivial aspect of the theorem. It's like maybe 1/3 of the content is in this part. So what was this mini PCP step? The mini PCP step is, if you recall, at the end of the powering step, you have this, oh, there's a question. What do you mean by stacking a graph? I literally mean like you have a vertex set. You had some original graph. It had like n vertices and it was some 8 regular graph. And now like just take another, sorry, it was 9 regular. Take an 8 regular expander on the same number of vertices n and just, call the vertices here 1 through n, call the vertices here 1 through n, and then just identify the vertices. So, and now every vertex has like its 9 edges from the original graph and like the 8 edges from the expander that you slapped on top. Or if you think about it in terms of adjacency matrices, literally sum the 2 adjacency matrices. Okay, hope that answered the question. Coming back to this mini PCP business, the output of the powering step was a CSP that was kind of crazy. It had this enormous domain size. You were assigning the vertices not red, green, and blue, but some gigantic label set, and had some complicated, albeit binary constraints. And the goal of this step is to get back to a 3 coloring constraint satisfaction problem. Well, okay, let's take a look. Imagine this white stuff here is like just a little teeny piece of the input CSP G. So remember, these vertices in G are supposed to be labeled from this gigantic set, doubly exponential in T. So if you think of like writing down those assignments with bit strings, you'll need like exponential in T many bits just to write down an assignment here. Remember, T is a constant though, so it's okay. And the constraint on this edge, it says something about how you're supposed to label these 2 vertices from this gigantic set domain. It may be so complicated that you should sort of think about it as being expressed by a circuit, which takes in 2 to the order t bits for this label and 2 to the order t bits for this label, and output 0 or 1 depending on whether the constraint is satisfied. Now, from this point of view, as I mentioned before, what you can try to do is re-encode this constraint with a PCP. It's kind of a recursive idea. Remember the PCP theorem, as we originally were trying to prove it, sort of reduces circuit sat to 3 coloring in such a way that, like, if you're like not satisfied, the resulting 3 coloring instance is sort of highly not satisfiable. There's some details here, like it's not quite as easy as this, and you actually need a slightly different object, not a PCP, but a PCPP, probabilistically checkable proof of proximity. But it's more or less the same. So I can only give you the high-level ideas here. But why is this not like circular argument? It's not a circular argument because in the PCP theorem itself, which is the thing we're trying to prove, you want a polynomial time reduction that takes a circuit and in polynomial time outputs like a graph that, you know, has some relationship to the circuit. But here, we don't mind about efficiency at all because the size of the circuit and the number of bits here is a constant 2 to the order t. So even if you have like a non-efficient, like exponential size or doubly exponential size PCP, it's fine. In fact, that's what we're going to use, a doubly exponential size PCP, which is why we get this crazy blow up here. Now, there's a funny question here, which is that normally in, you know, the world like this, you know, you're trying for a polynomial time construction, you know, it's trivial to get an exponential construction or doubly exponential construction, but it's actually not trivial at all here. In fact, it's not obvious that how to even do this. It's not obvious how to get PCPs of any size. Because it has to be like one construction of like a 3 coloring instance from a circuit, which is kind of oblivious to whether the circuit is satisfiable or not. Like the reduction cannot like first decide if the circuit is satisfiable and do one of 2 things. It just has to be one transformation from circuit to possibly doubly exponential sized 3 coloring instance, but which has the 2 properties about if it's satisfiable, it's 3 colorable. If it's not satisfiable, it's far from 3 colorable. So even though this looks like a much weaker task, it's not obvious how to do it. But prior to Dünner's paper, it was basically known how to do this. And I can only give you like a little bit of ideas here. But there's a not too hard construction of doubly exponential size PCPs, or even these PCPPs, that I can't tell you about more, but it uses 2 ingredients, error correcting codes and Fourier analysis of Boolean functions. So when I taught Fourier analysis of Boolean functions many years ago, I gave this proof in like 1 lecture. And let me just say, the main step is the Fourier analysis of Boolean functions. And particularly the thing you need is almost identical to something that was on your homework 3, number 5, your Nobel Prize in Economics, that part where you gave a Fourier analysis of Boolean functions based proof of Arrow's impossibility theorem. Remember that theorem about voting? Like if you have a 3-candidate election, you know, any voting scheme that like does all the 3 pairwise comparisons and tries to like figure out if A beats B or B beats C and C beats A and picks a winner, Arrow's theorem is that like the only way you can do that is by having a dictatorial scheme. So you prove that using Fourier analysis of Boolean functions. And that's basically, it's hard to explain why, but that's basically what you need for this mini PCP, exactly that. And somehow the idea is that like randomly having everybody vote and checking to see if there's a Condorcet winner, like A beats B, and there's like one clear winner that beats the other 2 candidates. It's kind of like a PCP for an election function being a dictatorship. So some kind of test that only looks at the election function outcome on 3 different strings, and it has one property, there's always a Condorcet winner if F is a dictatorship, and use Fourier analysis to show that if you're close to always having a Condorcet winner, then you must be close to being a dictatorship. So it's kind of amazing, but this like robust proof of Arrow's theorem that you get from Fourier analysis of Boolean functions, it's kind of like the most important ingredient in this construction of the mini PCP. So it's perhaps hard to have questions about that because I only gave it at a very high level, but I thought that was a kind of cool teaser that I could tell you about this last bit. Okay, so there's only one step left, the key step, the powering step, which has this parameter t. And this is the part that increases the badness in a three coloring instance. Okay, well, it transforms to a different kind of CSP. So the main effect of this powering step is to take a 3 CSP with a certain amount of badness and increase its badness by a factor of t. Well, so you get a factor of t divided by some universal constant. And the side effect, well, it will blow up the size by a constant, 2 to the order of t. And it'll also give you this like kind of complicated CSP with a gigantic, albeit constant size label set, and still complicated binary constraints. So let's see how this goes, and then we'll be done with everything. So here's the idea. You take this 3 CSP G, which has been made an expander, and that's crucial for powering. And the output CSP G prime is going to actually have the same vertex set. It's just going to have like many more edges. And as I mentioned, the powering operation is kind of like teeth powering the adjacency matrix. So the edges, aka constraints, in the new CSP G prime will correspond basically to length t walks or length t paths in the input graph G. You can basically think of G, by the way, as a 3 coloring instance. It actually has some equality constraints in addition to the non-equality constraints, but basically like 3 coloring. And we'll even do like the lazy version of walks, where you can also do a self loop. And so for every vertex in G and G prime, although it had degree 17 in G, it's going to have a degree which is something like 18 to the t in G prime, because it's going to have like a constraint for every walk of length up to t. And there'll be like, 18 choices at each step because it's a 17 regular graph, and you can also do a self loop. And the new domain is going to look like sort of strings over the symbols red, green, and blue of length like roughly 18 to the t, like the number of these possible paths. So that's why the domain size is this like 3 to the 18 to the t. Okay, so that's the story in the size and the domain, and like basically now I want to tell you what the constraints are and why they achieve this main effect, and that's going to be everything. Okay, so G prime, same vertex set as G, but like the edges / constraints in G prime are going to correspond to these like length t walks in the original graph. And the domain is going to be like these really long strings of like red, green, blue. And I should also say that like I'm now going to start to get quite hazy on a certain point. These paths, I said they're length t, but they're really like length around t. And try not to stress out too much about like what does it exactly mean like around t. It's like a bit of a point where you have to do some like tricks, which I don't want to get into. But just let them be like hazily, not length exactly t, but in the neighborhood of t. Okay, so what is the meaning of this new domain size? So in the G prime CSP, you'll have some vertex, let's call it U prime, and think of a label for U prime. Don't think of a string so much as just think of like U prime's label is supposed to represent an opinion, a quote unquote opinion on what U's, I guess U and U are probably the same here. I'm not sure I use different letters. On what U's neighbors at distance at most t should be labeled in the old graph. Okay, so a label in G prime for U consists of like a bunch of labels, of each label being red, green, blue, for like U's distance t neighborhood in the original graph. Let me try to draw a picture. So let's say this is like a piece of the original graph G, and let's say t is 3 for extreme simplicity. So here's a path of length 3 in the graph G. And so this will become like an edge in G prime. Okay, and I haven't said what the constraints are yet, but I'm talking about the labels now. So the point is that like the labelings, instead of labeling the vertices by red, green, and blue, you're now going to label them by like these very complicated looking things. Like a label for A in omega prime is like an assignment of red, green, or blue to all of A's neighbors at distance at most 3. So it might look like A should be red, B should be green, C should be green, D should be green, E should be red, F should be blue, G should be blue. And probably there's like more edges out here as well, but I just drew a piece of it. Okay, and in the CSP G prime, G will also supposed to be, this vertex here will also supposed to get like labels that look like a red, green, blue assignment for all of the distance at most T neighbors of G. Okay, and I call these opinions, and we'll use that terminology because that's how you think of them. Okay, so this is what the new graph is. It's got these like length T paths as its new edges. This is what the new label set is. It's like these big opinion sets. What are the constraints? Well, the constraints are actually the most natural thing. So like this AG is now an edge in G prime. And we're supposed to put a constraint on it about how these two kind of labels from omega prime should be given. And what you basically do is check all the things. I mean, check everything that would be logical to check. So the constraint checks a lot of things. First of all, it like, you know, A and G have some vertices that are at, potentially have some vertices at distance, you know, at most T from each of them. So there's some vertices, like let's say F, that are like opined about by both A and G, little g. Should have used little g as the key vertex, but anyway. So for example, A's opinion on F is that it should be blue. Little g's opinion on F is that it should be a green. And this is contradictory. So this assignment, this example assignment would falsify or like would violate this constraint because it would fail this check. But that's not all. The constraint between A and G in this new CSP does some more. For each edge UV in the original graph, like let's say EF, which is within distance T of both A and G, if like A is close enough to E that it has an opinion on it, and G is close enough to F that has an opinion on it, then you check that A's opinion about E and G's opinion about F satisfy this EF edge back in G, which is either a non-equality constraint or an equality constraint. So this is the definition of like these constraints. Actually, you really only need these ones. You don't actually need these ones, but you may as well put them in. Okay, so it remains to show that I've now defined for you G prime, and it remains to show that this powering step works, that like the badness in G prime is bigger than the badness in G by a factor of T. And I wrote like omega of T to denote like T divided by a universal constant. And again, provided the badness is smaller than an absolute constant. And I've switched to putting show in quotes here because like I've glossed over enough stuff now that I'm really just sketching, not showing. And so the argument is actually kind of similar to the argument we saw for degree reduce. You take an assignment A prime for G prime, and you say that like, well, I can get from an assignment A for G, that assignment A for G has to be violating a badness fraction of edges, and I'll deduce that A prime is satisfying like T times badness fraction of edges in G prime. So I have like a couple more slides sketching this, and then we'll be totally done. So this is what we got to show. And here's the start of the proof. Well, don't panic. So let A prime be the best assignment for G prime. And so A prime is like, for every vertex W, A prime consists of like a bunch of opinions for like the red, green, and blue for the neighbors of W, or the distance T neighbors of W. So let's write A prime of W sub V for W's opinion for V's color. So that's just red, green, or blue. And now we're going to define an assignment A for the original three coloring type instance G. A of a vertex is, to figure out what A's value for a vertex is, you basically look at all the paths of length about T starting at V, going to some different vertices W. And each of these vertices W has an assignment A prime. And since they're a distance T, like this A prime of W has an opinion about what V should be. So like all of these like distance T or more or less neighbors have like an opinion about what, a quote unquote opinion coming from A prime about what red, green, or blue value it should get. And you take the plurality opinion. Okay, so that gives an assignment A for G. Now like a little bit of bookkeeping. T is this distance parameter. Let epsilon 0 be 1 over T. And let epsilon denote basically denote the badness of G, whatever that happens to be. Except that if badness is already bigger than epsilon 0, then instead let epsilon denote epsilon 0. This is a minor point. Okay, so we know by definition of badness that A, this construction A that we got, violates at least a badness fraction of edges back in G. And in particular, that badness is bigger than epsilon, so it violates at least an epsilon fraction of constraints back in G. So just pick out any fraction, a set of exactly epsilon fraction of edges from G that are violated by A. You know, it's going to be at least epsilon, so just fix some set of fractional size epsilon and call that set F. So this is a set of edges back in G violated by A, and it's an epsilon fraction of edges. And finally, like before, like for each of these edges, we want to kind of show that it induces like kind of like bad path constraints in G prime. So this is our final goal here, which we'll do on, I think, the last slide. So this is our definition of the assignment for A, and we have this fixed set of epsilon fraction of edges back in G that are violated by A. Now, consider the following sort of thought experiment. Pick a random edge from G that's in this violated set F. I don't think of F as standing for fail. Okay, this edge is also in G prime. And now form a random path of length around T by doing like a walk of length around T from U, and let's say it ends at A, and also a random walk from V of length around T, let's say it ends at B. Now, this random path itself will have length like about 2T, but like, please gloss over this fact. Please like, don't worry about the fact that like, well, this path is length T, this path is length T, but I'm also gonna try to claim that this whole path is length T. They're all around T, like, don't worry about that part too much. So, this is like kind of a thought experiment. For every edge U, V, and F, imagine sort of extending it to like a length around T path in G prime. Now, this is also the procedure that's used to define A. You see, to get A's assignment to, well, let's look at V. To get us A's assignment to V, by definition, we kind of take all the paths, or like a random path from V of length around T, end somewhere, let's say B, and then look back at B's opinion on what V should get, red, green, or blue. So sort of by definition of this plurality assignment, when you like kind of take a random path of length around T starting from V, you get somewhere B, and you look back what A prime of B says you should assign to V. By definition of plurality, like there's at least a 1/3 chance that that opinion will be the plurality vote. So what I'm saying here is there's like a 1/3 chance in this thought experiment that A prime of B's opinion about V will be the same as the plurality A of V. And similarly for U. And when that happens, and this happens with a 1/9 chance over this choice of random two paths, or this random path from A to B, A prime violates the AB constraint that exists in G prime. So we have this constraint, it's a path of length around T, so we have a constraint between A and B in G prime. And one thing that is checking is that the assignment A prime, the assignment A prime to A, that its opinion on U, and A prime's assignment to B's opinion about V have the property that they satisfy this edge. But if they agree with the assignment A, and UV is an edge that A violates, then A prime is violating this A to B path constraint. And that happens for like 1/9 of all these paths. So thus, and I put this in quotes because I'm really getting a bit sketchy here, but this is exactly how the proof goes with a little bit of care. The overall badness, the fraction of path constraints violated by this best assignment A prime for G prime, is at least 1/9 the fraction of length T, or length T or so paths in the graph that pass through this set F of epsilon fraction of constraints violated by A. And this looks pretty good. All we need to show is that this is at least, T times epsilon. And it kind of feels good because, you know, you have these paths of length t that have around t edges on them, and intuitively, an epsilon fraction of all the edges are these like, violated edges from f, which is, and so like, you get a violation in G prime by A prime whenever one of these random paths like passes through like this set F. And if T edges, these paths, and an epsilon fraction of the edges are bad, so you kind of expect T times epsilon chance of a bad path in G prime. I'll say that in more detail at the bottom, but the only thing that could go wrong here is that, this set of violated edges F, they could be all like cornered up in like one piece of the graph. And maybe most paths in G evade this set of violated edges F. But this cannot happen finally because it's an expander graph, which was the whole point of expanderizing. So the picture here, the high level picture is you have these edges in F, they constitute an epsilon fraction of G. These are the yellow edges. And like you pick a random path of length of about t. And now, since you made G an expander, the edges in this random path kind of look like they're distributed uniformly. Like this is the key property of expander graphs and like spectral bounds. And if you do like a random walk, like pretty quickly you get to the stationary distribution. And like a typical edge that you traverse looks just like a random edge in the graph. Okay, so you need the expander mixing lemma to actually formalize this, but the point is, if you just now, because it's an expander, you can sort of pretend that each edge in this random length t path is like a uniformly random edge, and therefore it has an epsilon chance of passing through one of these violations F. And so the probability of a random path, which is like a random constraint in G prime, missing F completely is like 1 minus epsilon to the power of t. Which, by original lecture 2 or whatever about approximations, we know 1 minus epsilon to the t is basically the same as 1 minus t times epsilon. Well, provided, epsilon is smaller than 1 over t, but it is by this setup. So this says that the probability a random path misses F is like 1 minus t epsilon. So the probability a random path hits F is like t epsilon. And like we know that like if you hit a random edge, you sort of have like a a random path hits F, it has like a 1/9 chance that its endpoints are violated, get assignments that violate the constraint that you put on this path. Okay, so you get this divided by 1/9, and that completes the proof sketch. So sorry for going quite a bit over time, but I'm done. This completes the proof sketch of the PCP theorem. It also completes the course, so that's the end. That's our last lecture of CS Theory Toolkit. And yeah, thanks a lot for sticking through it. It was quite a memorable semester. Usually, like, in the last semester or the last lecture of like a course, I like to, bring in like donuts or like croissants or whatever. But I cannot do that because you're all at home in a lockdown. So the next time I see you, it's on me. So next time I see you in the fall or whenever, remind me of this, and we'll go down to Tatza and get like a chocolate croissant or something, and we can reminisce about CS Theory Toolkit. Okay, so as always, I will stop there, and but I'll stick around to answer any questions you might have.